All right, guys. Today we're gonna be looking at the third problem under the DFS pattern, and this one's a pretty famous pattern. You may have heard about it before, or you may have seen it on Leetcode. But today we're gonna solve it using what we have already learned in DFS and DFS pattern, and see how we are utilizing DFS or traversing the tree and being able to use that method to get our solution. So the question is pretty straightforward. It says, given a binary tree, return Boolean value true if it is a balanced tree, or Boolean value false if it is not. And one thing that strikes out here is the balanced tree definition. So the first thing in an interview, what the interviewer expects you to do is clarify what a balanced binary tree or a balanced tree is. So a balanced tree, by definition, is if the left subtree height minus right subtree height differ by at most 1 in magnitude. In other words, we can say if the height of the left subtree and right subtree are same, then it's a balanced tree. Or if the heights of the left subtree and the right subtree differ by at most 1, even then it's a balanced binary tree. If the heights of the left subtree and the right subtree differ by, let's say, more than 1 in magnitude, then this is not a balanced binary tree. So let's assume we are given this example that I have already tried to add here in the comments. This is the binary tree given to us. We just need to return true or false. So let's see what our intuition says, right? And let's see what result we get just by looking at the binary tree without even trying to think about how we'll code it out. So this is 1, 2, 3, 4, 5, 6, 7. These are all the nodes in the binary tree. And let's look at our condition. We need to check the height of the left subtree, and then we need to check the height of the right subtree. And very intuitively, let's forget about everything and just look at the heights of the left subtree and right subtree starting at the root node, right? Assuming that we are looking at this tree from a higher level, we are at this node, and all we want to know at this point is what the height of the left subtree is and what the height of the right subtree is, right? So the height of the left subtree in this case would always be the maximum height among the heights of the subtrees that we try to find. It is pretty common to have multiple subtrees within the left subtree, and then it's also common to have multiple subtrees within the right subtree. So if we only consider the left subtree of the root node 1, we would end up having multiple subtrees within that left subtree. And so the height of the left subtree overall is going to be the maximum among the heights of all the subtrees that exist, right? And so logically speaking, all we will have to do here is count the maximum height. So going from 1 to 7, we have 1, 2, 3, 4. The height is 4, right? The root node to the leaf node, the height is 4. This one, the height is 3, so we are going to consider the height 4. So the left subtree height for root node 1, right? The height of the left subtree is left subtree height is 4, as we just saw, and then the right subtree height is, let's do that again, right? Same thing, trying to calculate the number of nodes between the root and the leaf here. 1, 2, 3. It's 3. So looking at the tree from the root node alone, we can say that it's a balanced tree. But it won't work in cases when we have the left subtree which is not balanced, or the right subtree which is not balanced. Right? In this case, it is balanced. I mean, in this case, inherently the left subtree and the right subtrees are individually balanced. So we can confidently say that looking from root node 1, our left subtree height is 4, right subtree height is 3. They satisfies the condition height of right subtree minus left subtree less than equal to 1. Forgot to mention, it's just the absolute value. We're not looking for the larger or smaller one. So this satisfies the condition because they differ by at max 1, and so we end up returning true. But we would have to do this for all the subtrees that we can find in the left and right subtree. So let's see how it would go, right? And then now that we have done it for root node 1, we need to look for all the subtrees under 2 and under 3, right? So we say for root node 2, now that we have assumed that 2 is going to be our root node, 2 is the beginning of our tree, let's look at the left height, let's look at the right height. So the left height would be 1, 2, 3, right? So left subtree height here, assuming 2 as the root of the tree, would be 3. And then the right subtree height here, assuming 2 as the root of the tree, will be, let's do that, 2 plus 5. 2 this is the first node, this is 5 is the second node, so we have 2. So far, this turns out to be true. This turns out to be true as well, based on a condition here. And then let's move forward with our DFS, right? We have looked at the left node. Now we need to look at the left of left, which is 4. So considering a root node as 4, we look at the left subtree height under 4, right subtree height under 4. So the left subtree height under 4 is 0 because there are no nodes. And then the right subtree height under 4 is going to be 1. Again, this calculates to true because this satisfies the left subtree height minus right subtree height absolute value less than equal to 1. Okay. And then let's also do it for so this is how the DFS works. So we have 1, 2, 4. Now we have exhausted almost all the nodes going to the left. And then we'll have one call for null because 4's left child is null, but we're not going to consider it here because this is just a pseudocode. Going to get rid of it, and then we're going to backtrack from the null child to 4, and then we're going to call the right child of 4. So we're going to say 7. So we are at 7. So the left subtree height for 7 is 0, and the right subtree height for 7 is 0 as well because it has, well, no children. So this calculates to true as well. Then we trace back because there are no more child nodes to be covered. We go back to 4, and then we backtrack to 2 because 2 was the original caller for 4, and then we call right on 2. So now let's call right on 2, which is going to be 5. So assuming that 5 is the root node of the tree, let's look at the left subtree height, right subtree height. The left subtree height is going to be 0 again, the right subtree height is going to be 0 again as well because there are no child nodes for 5 here. Nothing else to cover, so we backtrack to 2 and then backtrack to the original caller 1 because 1 originally called 2. Now we call the right node on 1, right? This is how the DFS works. So now we have all the right nodes to cover under 1, so we call for 3, assuming 3 is the root of our tree, root node of our tree. We have the left subtree height as 0 because there are no child nodes for 3's left, and then the right subtree height for 3 would be 1 because there's only one node below it. So this amounts to true as well, right? And then we eventually call for 6 because there's no node on the right of 3 to be covered, so we backtrack to 3. We call 3.right, which is 6. 6 has again 0 and 0, which amounts to true as well. And then now we're going to backtrack to 3. 3 has already been covered. Backtrack to 1. Nothing else to call. So this was our last call, right? Do a AND operation on all the outcomes. So we have true and true and true and true. everything's true, so we end up returning true. All right, this was our DFS that we performed on this tree, and we just need to basically convert this logic into a recursive function. So again, I'm going to write the conditions that we used during our walkthrough. So conditions that we used, right, to evaluate this tree are going to be condition number 1. We are checking to see if the two things could happen here, right? We're checking to see if the tree, if the node is none, we just return 0, right? So we're not considering that here. That's the base case. The 3 conditions that determine if a tree is a balanced tree or not would be to say if the left height minus right height, ABS of left height minus right height, if it is less than equal to 1, right? Or inversely, we can say if it is greater than 1, then it's false, and this results in a false result. The second condition that we were looking at while walking through these conditions, while walking through these cases, was if either of them is false, right? If the left subtree is false or right is false, then we end up returning false, right? And then the very last condition here, which is the height itself, right? 4 returned its height to 2, 2 returned its height to 1, and so we need to return our heights so that 1 can use that height. What would be the height that 2 would return? It would return the maximum of its left subtree height and right subtree height. So we're going to return max of left subtree height and right subtree height, which are represented by left and right here, plus 1, right? Because we need to consider 2 as well. Return max of left comma right plus 1 to the parent node, or the parent, or the caller. Let's call it caller because 1 called 2, right? So these are the 3 things that we were looking at while walking through this example. Now let's try to replicate this into code, into a recursive function in JavaScript. So let's say we have a function, let's call it, we can call it balanced tree, is balanced, all right, and then we can say is balanced is going to take in the root node, all right, and then the first thing that we're going to check is if root is null. If it is null, we can just return 0. That's our base case, so let's label it as base case here. The second thing that we need to consider is the left and the right subtree heights. So we can say let left is equal to, or we can say left height, to name it better, we're going to call is balanced, and say root dot left. We're going to call it on root dot left. Say left right height, and say is balanced. We're going to call root dot right. Then once we are done calling, we know that our function is going to return the height of the left and right subtrees. It's either going to be these values. Again, what we want is to either have 0 or -1, right? Or it could be 1. So once we have those heights, now let's go through our conditions. This is the first condition that we are looking at. So we say if abs, or we could say math.abs in JavaScript, we would say left height minus right height. If that value is greater than 1, then we know that the tree is not balanced. So we just return, oops, I forgot the parentheses here. Then we return -1. There's one more condition to cover here, which is this one. If left subtree is false or if right subtree is false, we end up returning false. So we say if left height is -1, right? Or right height is -1, then we do have to return -1. So this covers this condition right here. This is the second condition. And the very last thing that we were looking at is what do we have to return to the caller. So we would return max of math.max of left height, right height plus 1, which is our third thing that we wanted to return to the caller. And so this is about it. So we're going to end up returning either a 0 or a -1, 0 or a 1 to the original caller. Whoever calls is balanced externally, and that would determine if our tree is balanced or not. 0 will signify a tree is not balanced. 1 is going to signify that our tree is balanced. All right, let's look at the time complexity here. So the time complexity here is going to be O of n, where n is the number of nodes in the tree, because as we can see, we traversed the tree and we visited every node at least once. So n is the number of nodes, and in space is going to be big O of n again, because we are recursing, and then the recursive call stack could be at max n, where n is the number of nodes in the tree. Okay, so in tree kind of questions where you're using recursion, you don't implicitly have to specify the space complexity. Time complexity is what we are looking for, and whenever it's a DFS or a BFS, depth first search or a breadth first search, we are always going to be visiting every node in the tree, so we're going to end up having big O of n as time complexity here. Alright, this was about it. We'll be looking at similar questions, more interesting ones, in the upcoming videos. Stay tuned, and I'll see you in the next one. Bye bye.